Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to talk about ionic bonds 4.20. Okay, we're going to review a little bit. First of all, we had chemical bonds. They're going to be bonds that hold elements together to make molecules or compounds. Now, we talked about there are three types. The first type is covalent bonds, and that's what we talked about in the previous episode. Today we are going to talk about ionic bonds, and then the next episode we'll take a little bit of time to talk about metallic bonds. Okay, so first thing we need to realize is that ionic bonds, it's not so nice as it was with covalent bonds. There's no particular sharing going on. In fact, one culprit is going to steal electrons from another person. Uh-oh. We're going to have to see who that is, who that culprit is. Now, they do occur between metals and nonmetals. And just like the name suggests, they are going to create ions. Makes sense? Right. So let's go back and remember that certain rules still apply. So the first thing we have is the rule of 8. And atoms still want to be happy when they have 8 valence electrons or when their outer shell or outer ring is filled. Makes sense? Okay, when we had covalent bonds, we're going to review a little bit from yesterday. So we had covalent bonds like hydrogen, and it was H2, and we saw that we had a shared pair of electrons. Sounds good. Now, we also need to review electronegativity. Again, this was a measure of how strong atoms attract electrons to themselves. So if this is an electron, we catch it and we hold on to it. Okay, so that's going to be a measure of how strong an atom is to attract. So who are the strong ones? Well, we'll find out again today. Remember, I just told you that ionic bonds are between metals and nonmetals. Well, let's look at the metals on the left-hand side of our periodic table, and you can see that they're yellow, and the yellow actually means that they're very weak. Remember, our trend is from the low to the high. So who's our strong, who's our thieves today? When we talk about ionic bonds, it's going to be our nonmetals. If you look at this periodic table, you'll notice that the red ones, the fluorine, oxygen, nitrogen, chlorine, okay, these are all of our strong atoms. And kind of odd because we often think of metals as being strong and nonmetals as being weak, but in the molecular level or the atomic level, it's the nonmetals that are the strong ones. Now let's do a little bit of talk about yesterday. So here's water, okay, with a very strong oxygen and a medium hydrogen, and we have an electron, and the oxygen kind of holds on to that electron a little bit longer. Every once in a while, it'll give it back to the hydrogen just to make sure that it's still sharing. Okay, not often though, but it does happen. Well, today, and we remember we had a partial charge of negative because the oxygen holds on to that electron more often, and we have a partial positive charge because the hydrogen gets that electron once in a while, but not so often. So he's often just sitting there all by himself, just a proton all by himself. Okay, we called that polar, and we said that it was unequal sharing of electrons. Now that's, again, they're still sharing. Now today is going to be slightly different. We're going to look at a very typical ionic compound, something that you're very familiar with. It's sodium chloride. So sodium chloride is NaCl. That's Na for sodium, Cl for chlorine, and this is just table salt. But kind of like we had yesterday, we have, instead of oxygen, we have chlorine, very strong, and we have sodium, really, really weak. So when sodium has an electron, and they have, if you remember, sodium has one valence electron, well, guess what? The chlorine's going to steal that electron and not even share it. They're going to not even give it back. So they're going to be a we're going to find out soon that they're going to be an anion, and the sodium is going to be a cation. So again, let's look at sodium chloride from a Bohr model standpoint, and we have sodium and we have chlorine. Now, even though chlorine has more protons and neutrons in the nucleus, its atom is actually smaller than the sodium. What happens is that the chlorine is strong and it holds its rings closer to the nucleus than the sodium does. The sodium's actually kind of weak, and it actually lets the electron cloud get larger because it's not strong enough. So, interestingly, when I see most of the models, we see that people point to the larger chlorine models and say that that's the larger of the two atoms. Well, in fact, it's the sodium that's a larger atom, and the chlorine is smaller. In fact, it's close to 2 to 1. Now, I didn't draw it quite that way because that would be quite a bit different, but I drew it kind of in the middle. But just for curiosity or clarification, that sodium is actually a larger atom than chlorine is. So what's going to happen here? Okay, let's look at our Bohr models. We have sodium on the left, and that has 2 electrons on the first energy level, and it has 8 on the second. That gives us 10, and then it has 1 on the third energy level. Okay, so that's what we would see. Remember, sodium's in group 1A, so it's going to have 1 valence electron, and that's what we see. Now, chlorine, on the other hand, is in group 7A. It's going to have 2 valence electrons not 2 valence electrons, 2 electrons on the first energy level, 8 on the second energy level, and then it has 7 on the third energy level, which would be its valence electrons. So that would be 7. Now, what happens here is that sodium will give up, or let's put it the other way, chlorine is so strong that it steals that electron. Let's watch that again. See if I can do that. I can't. But so we have that the chlorine steals the electron from sodium. So now sodium has 8 electrons and on its outer shell, and so does chlorine. So let's count these up. There's 4, 5, 6, 7, and 8. So chlorine is now happy. Sodium, 1, 2, 3, 4, 5, 6, 7, 8. Now we have to go into the second energy level to get 8 valence electrons. So if we look at it this way, sodium is also happy. Remember the rule of 8. They're looking to fill their outer shell, and sodium fills its outer shell. It doesn't have a third energy level anymore, but it goes back to the second, and chlorine does in fact, fill its third energy level. All right, now let's take one more look at this from another model. Let's look at the Bohr model. Excuse me, this is the Lewis dot diagram model, pardon me. And we have sodium and chlorine again. And what happens is that sodium will give away its electron to chlorine, making sodium a cation and chlorine an anion. And remember, when we draw the Lewis dot diagrams, we need to put the brackets on when they become ions. Again, sodium is going to become a cation, so it gets the brackets. And notice that it has no dots on its inner square. And we get the square brackets and a +1 because it gave away 1 electron. And chlorine, on the other hand, is an anion, and that also gets the square brackets. It has all 8 electrons on its box, and it gets a -1 charge. That makes it an anion. So let's look at a completely different one. This is going to be aluminum bromide, and that symbol is going to be AlBr3. Now, how do we know that this is going to be the formula? Well, let's look at aluminum. Okay, so here's aluminum, and we have 3 valence electrons. Remember, aluminum is in group 3A, just like our friend boron, so it has 3 valence electrons. And if you recall, when we were talking about covalent bonding, we talked about pairs and spares. Well, this one is going to have 3 spares. And you can see them here. So I'm going to put them in green for a second. Okay, now that's saying, if we remember how we did this, that I have 3 available spots in my parking spots. Okay, so 3. Now, unfortunately, when aluminum's in the presence of other anions, like nonmetals like bromine, okay, it's actually going to want to not really have those 3 spots. But here comes our 3 bromines, and the bromines are actually going to not park there, but they're actually going to steal those electrons. So here's the 1 that's stolen, 2 that's stolen, and 3 that is stolen. So now let's look. We have aluminum, which is now kind of naked because it doesn't have any electrons on it, but that's going to be a cation. It's going to get the square brackets and a +3. And then our 3 bromines, they gained electrons, so they're going to get a square bracket and a -1. So aluminum had 3 electrons initially, and since it's a metal and it was hanging around with bromine, okay, bromine's way stronger than aluminum is, so bromine actually steals those electrons. So that makes aluminum a cation. All right, now we're getting close to the end here, but let's look at some structures here. Now remember, why do aluminum and bromine attract each other anymore? Well, it actually comes down to something called an electromagnetic force. And we've already talked about this at some point. And you know that opposites attract. So I have a positive aluminum, and then I have a bunch of negative bromines hanging around. And just like always, opposites attract. So I have a positive attracts a negative, very much like the nucleus of the atom attracts the electrons, because the nucleus is positive because of the protons. Same idea here is that the aluminum is positive and the bromines are negative. Now it turns out that instead of we look at the structure, we actually get it so that they are attracted to each other. So they make these lattices, which is what it's called, and it basically forms crystals that would look something like this. Now, this is a picture that I found online that showed sodium and chlorine. Again, when they went to reference this, they said that the sodium atoms were the purple ones and the chlorine atoms were the green ones. And I don't really think that's correct. Um, I think that the green ones are actually the sodium atoms, and the purple ones are chlorine because of the other research that I've done. Okay, so when we get this structure, we actually get a crystalline structure, and this is a picture of salt granules that are really, really magnified. So that's something that's kind of cool with the ionic structures. Okay, they actually form these lattices, these long chains of um, of positives and negative charges all attracting each other. Okay, now some of the cool things that they do is they produce some really cool crystals. So here's some pictures of crystals that I just thought were pretty cool. I pulled these up online. All right, let's do a little final review and we'll be done for today. So, first of all, ionic bonds occur between nonmetals and metals. Now, the nonmetals are strong. They will steal electrons from the metals, and then both of them will become ions. The metals will become cations, and the nonmetals will become anions because they gained those extra electrons. Nonmetals steal valence electrons from the metals. Okay, we just talked about that. And ions are created. And then the really cool part is that when they do that, they produce really cool crystalline structures. Oh, just for the record, this is my arm. And no, it was not photoshopped. Good try. As always, that's Chemistry on the Fly for today with Mr. F. And as always, have a great day. Electrons.